Welcome back to the lessons for electrochemical cells. In the last lesson, we learned that reduction happened in one half of a galvanic cell and oxidation happened in the other. A wire allowed electrons to move from the anode to the cathode, while a salt bridge kept the two cells electrically neutral. Now, there's a very simple calculation you can do to figure out how much energy a reaction gives off, just by looking at the numbers on the table of standard electrode potential. The numbers you see there are called standard reduction potentials. Why standard? Well, that means that the voltages are all recorded or measured at the same conditions. Those are 25 degrees Celsius or 298 Kelvin, 1 mole per decimeter cubed concentration, and if there is a gas involved, 1 atmosphere of pressure. If you look very closely at the table, you'll see a reaction in the middle that says 0 volts. This is the reference reaction of hydrogen ions and hydrogen gas. It's called the standard hydrogen electrode, or SHE. It's used as a central place to compare the other materials for their ability to reduce. The big problem with the SHE is that the hydrogen in the reaction is a gas at room temperature. So a platinum metal surface is used to allow the hydrogen gas to react with the solution. Platinum is very good at holding onto platinum and often acts as a catalyst for reactions involving it. Scientists have agreed that even if the SHE is the anode, it should always be drawn on the left. Use 1 mole per decimeter cubed for hydrochloric acid and have a gas pressure of 1 atmosphere applied. The solution should also be kept at 25 degrees Celsius because the temperature can affect the readings and change the voltage. On the other side, another substance in both oxidized and reduced forms is placed and electrically connected to a voltmeter and a salt bridge. The SHE is used as a way to measure the ability of all the other substances on the table for their ability to undergo reduction. That means a very positive number means that it's very likely that reduction would take place. A negative number means that reduction is less likely to take place. These are more likely to oxidize. So, we find out that the substances on the top right are likely to be reducing agents, and the bottom left will likely be oxidizing agents. In this example, we are trying to find the reduction potential of magnesium. If all of this seems complicated, don't panic. Scientists made an easy way to use the redox table for good. They used the formula E naught cell is equal to E cathode minus E anode. That means the voltage of a galvanic cell is found by taking the voltage from the table of the cathode and subtracting the voltage of the anode. So, reduction minus oxidation if you would prefer it in that way. This cell has got two parts to it: an iron electrode with iron 2 nitrate on the left and a lead rod in a solution of lead 2 nitrate. There is a salt bridge between the two with sodium nitrate inside. We are asked to find the half reactions occurring, calculate the voltage measured at standard conditions, describe the electron flow, label the positive and negative terminals of the cell, and finally to write a net ionic equation for the reaction. Okay, first things first. Identify all the species on the table. We see iron metal, Fe2+, is present in two places. Water is always there, and we have lead metal and lead ions. Notice how we didn't circle the nitrate ions. This is because the nitrate ions require a hydrogen ion to be oxidizing agents, so they don't participate in the reaction. We call these spectator ions. Once we've got those circled, we select the strongest reactants from each side. Iron metal on the right and lead metal on the left. Now we write out the equations, making sure that we start with the species we selected. So Fe goes to Fe2+ plus 2 electrons, while Pb2+ plus 2 electrons goes to Pb metal. Now, while we do that, let's write down the EMF values on the redox table. Then we'll see how to use them in an equation. Now, to find out the voltage, substitute the voltage of cathode and anode into the equation. So negative 0,13 for the lead cathode half reaction and negative 0,44 for the iron half reaction. The total cell voltage works out to be positive 0,31 volts. The reason we've used brackets is because the negative signs can often give you algebraic problems. There is something very important about this EMF or voltage. First, it's the amount of energy given to electrons, but more importantly, a positive value tells us the reaction is spontaneous. If the value is negative, energy will be needed to keep the reaction going. The complete ionic reaction goes as follows. To label the positive and negative electrodes in a galvanic cell, we need to remember that electron will always go from a place of excess to the place that uses or lacks electrons. So the ion that loses electrons makes an excess. They flow to the lead reaction where they are used. There is a very handy note that helps us remember how to draw cells in the correct format. The word lone. On the left, we draw the oxidation half reaction. It's the anode and it's negative, but only in the case of the galvanic cells, so be careful. The anode isn't always on the left either, even though that is convention. So, the really interesting thing is that we can change the voltage of the cell by changing the conditions. In general, a higher temperature means that the reaction has the energy needed to move ions and overcome activation energy. So higher temperatures generally mean a higher EMF. Concentration is a tricky one, and we have to look at the half reactions to see if the change occurs to a product or a reactant. We need to remember that we only write one arrow for the direction because the forward reaction is spontaneous. If we add more reactants, it makes sense that we would encourage the forward reaction further. But what about adding a product ion? like the iron 2 ion. If we added more of that, we are actually working against the forward reaction that makes the voltage. That means a decrease in EMF, so be careful when you decide how a change in concentration would affect the performance of the cells. It's also worth noting that concentration of spectator ions and surface areas of the metals do not affect the EMF. Well, now that you know how to change chemical potential energy into electrical energy, let's turn our attention to electrolytic cells in the next lesson.